All right, here we go. So that's a question that will be answered later. All right, pre-cal, chapter 8, notes. So we're going to be learning about vectors. All right, so Jonah's the only one who took physics with me. He should have been here today. I would have called on him every question. No, we're like paused. Vectors, number, and direction, where scalar is just the number. Yeah, we're back. So A was a vector because it was given direction and number. B was just a scalar because it didn't say whether it was going towards the crowd or the opponent. It didn't give a direction. C is a vector because you have a number, 100 meters, and a direction, north. All right, so vectors are usually represented as an arrow diagram or a directed line segment. Look at the vector shown below. Cool. A is the initial point, also called the tail. B is the terminal point. It's where you end. It's called the head or the tip. So we write the vector as A to B. So notice there's like a little arrow at the right end. I don't know if you can see that very well, but like right here, there's like an arrow at the end.
It's a ray.
Yeah. Or we can denote it as like A with a ray, or A, if you're in physics, maybe he's used this notation with like a V with a little bar over it that stands for vector. It's a velocity vector. It's like half.
Because it's ray.
And then if you want the average velocity, it would be just the line. Cool. All right. Yep. That's fine. You know what? I'm going to help you with physics right now. A vectored in standard position is one that has its initial point at the origin. So here's my initial point. And we measure from the x-axis up. So it's kind of like we covered this before almost, like in chapter 4 when we studied trig. Right. Trig's beautiful. Okay. Just make sure you're focusing. If you guys are off topic, I'm just going to mark you down. I'm over being your parent, and like, I'll micromanage you if I must. I will. If you're not on topic, you're going to lose participation. That's it. All right. Vectored in standard position. The direction of the vector is the angle, and the magnitude is the length of the line segment.
Question.
So here, just a moment. So here, let's see. I have 35 degrees. That's going to be my direction. And then this length, well, I know 1 centimeter is 5 feet. So if I measure how many centimeters he is here, it's like 2.6 centimeters. You would like measure it out, which I did. So 2.6 centimeters. So, because I knew the scale. So I could say the vector above, 1 centimeter represents 5 feet. So 5 times 2.6 is 13 feet per second. That would be the vector. Because here it's saying 1 centimeter is 5 feet per second. If you measure out your paper, it's going to be 2.6 centimeters. So you take 5 times 2.6, you get 13.6 centimeters per second at 35 degrees. So that would be the vector. All right, you have a question?
Yeah.
What? Yes?
So, why does it say like it's the tail if it's the initial point, and like it's the head if it's the end?
All right, I want you to draw a line, and at the end of the line, put the arrow. Okay, so you see where you started the line? That's your tail, that's your end. That's where you started, but where you ended was where you drew the little arrow portion. So that's the tip, you ended at the tip. And later when we're adding vectors together, that's going to be important. We're going to be doing like tip to tail. Okay. Right. All right, so bearing. The direction of a blank is sometimes expressed as a blank. What do we think this word would be?
Bearing. The direction of a ray. The direction of a vector.
Yep, vector. The direction of a vector.
Vector scalar.
The direction of a vector is sometimes expressed as a bearing. Surprise. Making this more fill in the blanks. You have to pay attention. All right, a bearing, guess what? That's just another way to express direction. a quadrant bearing. So this is phi. This little guy right here, that's phi.
Phi?
Yep. So it's kind of like you draw a 9, but instead of going straight down, you go through the middle of it. There you go. Just taught you how to draw phi. That's a quadrant bearing is a directional measurement between 0 and 90 east or west of the north-south line.
Oh, I think I got it.
So instead of drawing a 9, draw the circle and then go through the middle of it. That's the way.
Hebrew letter.
Well, I mean, it's a Greek letter, so that makes sense. Hebrew is an old language, as is Greek.
Wait, isn't it pronounced phi?
Phi.
B.
Yeah.
So is it just a line between the 90 degrees?
Exactly. So it's the north-south line. It's literally your angle from the north-south line.
Oh, that's phi?
Yep. So that's your bearing, because normally when we say directions, we go from the x-axis around. Remember how we did terminal angles? Yep.
My Alex topic.
Perfect. That's a good idea. For Alex this week, pick vectors. There you go. All right. So here the quadrant bearing of the velocity vector v is 35 degrees east of south. Okay, so east of south. So if I'm pointing straight down south, east is to the right. So if I'm 35 degrees to the right, what would my actual angle be? How would we find this?
Well, that's 270. So then 270 plus 35 is.
Okay. So it'd be 305. So it'd be 305 degrees from the origin. Another way we could say it is, it's also, let's see, 180 minus 45, that's how we got 35 degrees. Because we knew this angle was 145, and we know going all the way over is 180. Okay, so a true bearing is a directional measurement where the angle is measured clockwise from north. So a true bearing is clockwise from north. Clockwise goes to the right, just like a clock. You're going around to the right. All right, it's always given 3 digits, so a direction measuring 25 degrees clockwise is expressed as 0 to 5. Cool. All right, so these lines, all of these vectors go with the next thing, which is parallel. All right, so
Why is it 0 to 5?
because it is expressed with 3 digits instead of 2.
So it's just 25?
Right, it's 25, but we say 0 to 5. Because imagine if you're an airline pilot and they're like, okay, turn to 25 degrees from north. Okay, so 25, was there a digit missing, right? Did the radio skip out? Did you mean 225? Did you mean 125 or 25, right? So that's why they say 0 to 5 is to be very specific. That way there's no room for doubt. Because technically you could have 3 digits, right?
It's if you know that that's how you're going to speak, then it's easy to conceptualize.
Yep. So that's where it comes into play. All right, so parallel vectors. So notice these are all vectors. They all have a magnitude, which is the length of the vector. They all have a direction, which is which way they're facing. And then let's see if we can find parallel vectors. They're the same or opposite direction, but not necessarily the same magnitude. So they're literally the same slope. Yay. Parallel vectors, parallel lines, they have the same slope. Cool. Okay, that's what we're looking for. Okay, so which ones are parallel? Do we know?
A, B, C, D, and then usually going in different directions.
A is parallel to B.
You write the line.
A is parallel to B, which is parallel to C.
I'm writing it pretty.
Parallel to E, which is, and then
E and F.
they're all going the same direction.
Oh, yeah.
They're all parallel to each other because they don't necessarily have the same magnitude. They don't have to have the same length, but as long as they have the same slope. They could be going the same or opposite directions. So here, the negative slope would match the positive slope. Because for us, the direction is just the arrow, which way is the arrow pointing, but they're all going from left to right. We're like going up. So they have the same slope. It's just like, oh, well, the arrow's actually pointing to the bottom left corner instead. So highlighted them all. They all have the same like slope. Yes?
What if we did like the little arrow above A, B, C, E, and F, if we did it like an arrow and not like half the arrow, is that correct?
Technically no.
The line. Okay.
Technically it's.
So you do like an airplane.
Yeah, it's like if you took an arrow, like Ninja Warriored it in half, you take the top half. Fruit Ninja it. Alright.
I missed that game.
I don't.
Alright.
I have it on my phone. Don't play it.
Couldn't you cut the fruit into fourths too?
I always try.
Yep, you could. Alright. And focus, because we are finishing this lesson next class. Alright. Equivalent vectors have the same magnitude and direction. So which ones not only have the same direction, but they're the same size?
That's not true.
The A and B have the same length? No.
No, they don't. C and E is math.
No, they have none of the same direction.
A and C and E.
A and C are both going the top, going to the right.
We don't have measurements.
Well, get out your ruler and you will have a measurement.
But I thought, like proofs tell you that you can't make any assumptions.
If you get out your ruler, you'll measure and you'll find they're the same.
No, you have to do this. You like take out the lead.
But even the ACT says like if there's no dimensions, it's like
Right.
That's what I was doing with SAT.
Okay. I hear what you're saying, but you're missing the point, Jenna. I hear what you're saying.
like how am I supposed to know that for sure?
So in the problems that we do, you will know the exact lengths.
So just like an example.
I'm just trying to show you guys what equivalent vector means. Same magnitude, same direction. Missing the point. Okay. Just like same magnitude, same direction. That's all we want. Opposite vectors. So opposite vectors have the same length but opposite directions. So
Could it also be
did I tell you?
E not the same size?
E and E is the same thing as negative A because, well, also you could say like E is also equal to negative C. Because E and C are going opposite directions, right? We see they're going opposite directions.
Yeah.
But they're the same length. So we say that they are opposite vectors.
How did you decide that like A, B, and Y?
Can you do C?
Well, I also put like negative C. You could also say A is equal to negative E.
Okay.
C is equal to negative E.
You just have to make one of them negative.
Yep. All right. What happens if you add opposite vectors? Like if I added.
It's 0.
How do you know this?
They're the same thing in one.
They're the same. Look at you.
Because we said they're the same length.
Wow.
When we add opposite vectors, we get a 0 vector. So for example, if I take A plus, if I add like negative A, I get 0. Awesome. Oh, jeez. Okay. Do we have any here? Oh, no, we did have some. Maybe by Haley. By Haley. Haley, are there Kleenexes by you?
Oh.
Yeah.
So they're the same thing. Thank you. Mr. Brian, why did you make the C negative?
Because it's going the opposite direction of E.
What?
So E is equivalent to the negative.
Either E or C negative.
Yep. Because then by putting the negative in front, it flips the direction and makes it equivalent. All right. Do we have any more questions about this? Any more questions about this one? Yep.
Estimating the equivalent vectors, it was A equals C, but could you add a third equal sign and put either two?
Equals negative E.
Yes.
Negative E.
We're almost done with this lesson.
I'm trying. I'm trying, so. That, yeah. Well, I tried building in extra time. Because it would be nice to, like cover the first and second section in 3 days and then have a day to review for the quiz and work on homework. That would be great. Do we have any more questions?
No.
Yeah. Go outside. Go outside. Blow your nose outside.
But I won't have a hall pass.
If you find me on it, I'll charge you.
No, because you told me I have to over them, and I don't want to.
You are.
One foot inside.
That's literally like when you get up, walk out of the room for like 20 minutes. Like, yep, bathroom pass. Like right now. I mean,
Like, if you have a mental breakdown and you need something, I'm going to go.
like we can talk about this one-on-one. Cool. All right. Yep. This is lovely. I hope you guys love the screencast. This is great because then I don't have to do it at home and you guys have to sit through all the baloney. All right, resultant vectors.
You just do it in our class.
No, I did the others well. That lets me know that you haven't seen the screencast.
Oh.
I don't think, well, she's been in class.
Exactly.
That one's just a sponge.
I watched Miss Malikian's.
Cool. The 6.2
Yeah.
because I uploaded.
Literally an hour shorter.
Yep, that's true. Yeah, that was her honors screencast, and then I split it into 2 days for you guys. That's yeah. Resultant vectors. When two or more vectors are added, the sum is a resultant. So you add two things, what's the result? Aha, it's the resultant. Add two vectors, the answer will be the resultant. There are two methods to find resultant vectors, triangle method or parallelogram. All right, so triangle method. This is what I was talking about earlier. Why did I talk about like the tip of a vector and the tail of a vector? Because when you add them, you do tip to tail. So if I have A plus B, I literally put the arrow tip to the tail of your second vector. Cool. And then guess what? The resultant is the vector from the tail of A to the tip of B. So the resultant will be this guy. All right. B, let's see, parallelogram method, you do tail to tail. So you did the tail to tail here. And then once it touches, you complete the parallelogram. Just like copy this over, copy that over, and then the resultant is the diagonal. So that's this guy right here. It's the diagonal. There's two ways to do it. I mean, I think, I don't know. My preference is I like the triangle method. It's way less things written on your paper, but whichever is easiest for you, that's fine. Can I do the example to explain it? Okay. Because it's better, like, talking about it, 0 stars. Doing an example, I think you'll get it. Example 1. Find the resultant of each pair of vectors using either the triangle or parallelogram method. State the magnitude of the nearest centimeter and direction relative to the horizontal. All right. So I have V and I have W. So I'm going to take, okay, so I know this is like cheating, but I'm going to, I should have done this in one line. Okay, so I'm going to grab this vector, move it over.
Are we allowed to bring a ruler to this test?
Yeah?
Oh. Nice, that's cool. Wait, you can do that?
I can, but
And now? Draw something.
surprise, I've done it before. Okay, cool. Let me change the color so you can see. That first one should be red. Let me make it red. Okay, so that matches. This guy should be blue. Okay. So I took V and W. So I have V and W. So this is the triangle method. For V plus W. So I took my first angle, I took my first vector. I redrew it. I took my second and I put the tail on the tip of my first vector. So, like, it might be easiest for you guys, like if you had a ruler and a protractor. I mean, you do know how to use it from geometry.
You didn't know where. They told us not to get them.
Awkward. Okay.
Not to get what?
Is tail to tail the same thing as tip to tip?
No. Well,
No.
no. That's not.
Wait, so the diagonal.
It would. Well, I think it would be the other side of the parallelogram, though. Okay, so
So the diagonal one always like stems out of the origin. Oh.
yeah. And if I connect the tip of V to the tail of W, oh my gosh, if only I could draw a straight line. This is the resultant, which is the answer. And so if you measured this with a protractor, you would find that this angle is 60 degrees. And if I'd actually, do I have a ruler here? Let me see if I do.
Are we gonna need to
Can I measure this? No. Man. What's wrong?
Are we gonna need to be like perfect?
I mean, ideal. If you would measure with a protractor.
But like when you redraw it, how do you know who drew it?
So you come over here. You see the angle here. You see the length of V. Here, you see, okay, it's a 90 degrees, and you find the length of W. Come over, translate. Well, I find I didn't give you problems on your homework where it was like, you must measure and blah, blah, blah. Like if there's like, there might be one that slips through. But I'm more about if I give you the dimensions of V and W, you being able to find it that way. And so that's the next thing is we're going to like break it down by components and angles because that's more important. Because like I could give a fourth grader this problem, teach them how to use a protractor, and like they could do it. But they could not do the trig and the breaking down components like you guys can. So. Okay. I don't find as much value having you guys like measure this because this is like this juvenile, like you've been doing that in middle school. Like why are you taking this class if all we're doing is measuring? Yep. All right, so I just have to show you how to do it. So this is like 3 centimeters. So if I want to write the resultant vector, so I write R as a resultant vector, it's going to be 3 centimeters at 60 degrees. Okay. Did I like go into the next problem? No, I did not. All right, so that would be the triangle method. I could do the
answer?
Yep. So if I would get out a ruler and measure on your paper. Yep.
Wait, is it a circle?
Nope. That's literally if you got out a ruler and measured the length on your paper, if you drew it correctly.
Oh, so it's just
Yep. So what percent am I at right now? If I go down to like, let's see, it needs to be smaller. If I go to like your paper, like it would be exactly 3 centimeters if you did it correctly.
How do you know?
Here's your paper.
Yeah. Alright. Let's see, this should be It's all good. How you got it? No, 6 centimeters. Huh? I don't get how you got 60 degrees.
I really don't think any of us drew it correctly if we have the ruler.
What gave us exact? Yeah, Gabriel.
So tall. I went over to Gabe and it's 3 centimeters.
Gabe, you don't even.
Where did you get 3 centimeters from?
I just measured his resultant vector. I literally went up to his resultant vector, measured 3 centimeters.
That's like genius material.
So, good job. Okay, if I take this next one, what did I not already describe how to do it? Alright, so you go to the vector. You go with a protractor and you find out what this angle is. Then, with the bottom of the protractor, because as a ruler, you measure the length of this vector. You note it down. Alright, and then you come over here. You find the length of W. You see it's at a 90-degree angle. So, I'd go and draw my axes. I draw my first vector at whatever angle it was and whatever length it was. Then, from the tail of the first one, I will draw my second vector to however long it was and whatever angle it was. Then I connect the tip and tail, the tip of V, the tail of W, connect it. I measure how long that length is with the bottom of the protractor, and then with that same protractor I find that the angle going to my resultant is 60 degrees.
Does it have to be parallel to the y-axis all the time? For the W?
No, it won't be. It just here, this is 90 degrees. The angle from W, it's 90 degrees.
Oh, so between W and V has to always be 90 degrees.
No. It's just because W is straight up, and that's a 90-degree angle.
Oh, that makes sense. You keep it the same direction. Okay.
Yep. So for me, I got mine exact because I just like traced over it and moved it over. That's something, that's something you could do on the homework paper I gave you, like, trace over your vectors. Nope. I don't want you doing it during class when I'm trying to teach you. Yep. It's like I thought of this. Alright, so B. Guess what? What do you notice about negative A and A?
They're 0.
Yeah, they're opposite vectors. If I do A plus negative A, that's 0. It's a 0 vector. Alright. Okay, so multiplying vectors by a scalar. If a vector is multiplied by a real number, scalar, so it means by any number, the scalar has a magnitude of absolute value k times absolute value of v. Its direction is determined by the coefficient k. So if I have a negative scalar and multiply by, what happens to the direction? Multiply by negative, it switches direction. If I multiply by a number larger than 1, it gets bigger. Multiply by a number less than 1, smaller. What about a positive number larger than 1? Bigger, same direction. What about a negative number less than 1? Smaller, and in the opposite direction. Okay. Why does it switch direction? Because negative. Okay, ready? Face the wall. Face this front wall. Alright, now I want you to turn 180 degrees. Exactly. So by multiplying by negative 1, it literally flips at 180 degrees. Switches direction. Total opposite. Oh. Think of a number in your head. Any number. Multiply by 2. Is it get bigger or smaller? Bigger. Okay. Think of that original number. Multiply by a half. Bigger or smaller? Smaller. So if you're multiplying by a number smaller than 1, it gets smaller. Multiply by a number bigger than 1, it gets bigger. Alright, so, and that's kind of what I was talking about. If you are multiplying by a whole number, it gets longer. It's a bigger magnitude. It's a longer vector. You're multiplying by a fraction, aka a less than 1, it gets a shorter vector. It's a smaller magnitude. For example, multiplying vector A by 3 will produce 3A. A vector 3 times as long, but in the same direction. What if I multiplied A by like negative 3? What will happen then? Exactly, it'd be the same length, but I'm going to switch direction. Oops, I didn't quite get this perfectly. There, this is negative 3A. It's the exact same length, just total opposite direction. Okay. So far, so good. So let's try example 2. Draw a vector diagram of 3x minus 3/4 y. Okay, so the first thing I would do is measure how long x is. How long is it? Dude, we don't know. What? Here, measure how long it is.
In centimeters?
Yep.
Two and a half.
2.5?
Yeah.
So multiply by 3, it will be 7.5 centimeters long. Cool. So the first thing we're going to do is we're going to rewrite as a sum because we know how to do vector addition, not subtraction. So I'm going to write it as 3x plus negative 3/4 y. What's the length of y? Will you find that for me?
Yeah. It's 3.2. It's supposed to be these like weird decimals.
So it's 3/4 times 3.2.
Are you sure about that?
No, what'd you measure it as? Huh?
You measured the top one as 1 and the bottom one as 2. The first one is definitely bigger than the second. And yeah, sorry, I need glasses.
The top one's 1 centimeter. I believed you.
What?
I believed you.
Sorry, everyone.
Sorry.
2.4.
So we're at 2 centimeters.
If we all come to a consensus, like, okay, x is 2, then, like, isn't it right? If we say x is 2, no, drawn by scale.
What?
Does it really matter? 1.3,
Yeah.
you need to know.
Yeah.
Like, 1.2, 1.3 for the top one. It's perfectly.
It's exactly 1.
No, I'm not.
Alright. So if I multiply by negative 3/4.
So is your column done already?
No. Next one. Alright. We can, because guess what happens? It's gonna flip directions. That's what the negative means. It's gonna be opposite direction and 1.5 long.
Are you counting the y as 2 centimeters?
The y is 2 centimeters.
Okay.
Alright, so I rewrote it as a sum. So the first thing I want to do is draw 3 times x. Move this. We're going to make it 3 times as long. So how you would do it on your paper is literally draw a line that is 3 centimeters long. Okay, so I drew mine 3 times as long. I'm going to copy this other one over. I'm going to flip direction. I'm going to flip the direction. And then I'm going to make it shorter. So it used to be, let's see, 3/4 shorter. So something like that.
How much shorter are you doing?
It should be 3/4 as long. So it's going to be 1.5 centimeters, but in the opposite direction. Okay, so this is negative 3/4 y. This one is 3 times x. And lastly, if I wanted my answer, I go from the tip of one to the tail of the other. Yeah, it's coming. This is the resultant. Sometimes the lag is like half a second. Sometimes it's like 5 minutes, just like now. Right, so class is over, but if you want it, so all we had to do is draw the vector diagram. So all we had to do is draw this 3x minus 3/4 y, and then this is it. This is all we had to do. But make sure you label. We'll finish this next time, and then we'll get going on 8.2. I'll give you your homework before you go.
Oh wait, so it's not in a textbook anymore?
Yes! I made.
Oh my gosh, it's not in the textbook anymore.
Okay, I made these